Okay, so I messed up this recording, so I'm just going to go through what I've already written. Um, in this one, we are going to look at a new definition. We're going to look at what are called normal extensions. And so what is a normal extension? An extension is called normal if whenever you have an irreducible polynomial over the base field, f over k, such that it has at least one zero in L. So f is irreducible with one zero. Then it must split entirely in L, which means that actually you don't just have one zero, you have all the zeros. So this is an all or none condition. You either have all zeros or you have no zeros. The simplest example of a normal extension is just if K is a subfield of C, just take C over K. That's normal. Why? Well, C has zeros of everything, right? So whatever irreducible polynomial you have, the zeros are already going to be in C by the fundamental theorem of algebra. So let me even say by fundamental theorem of algebra. So that's easy. An extension which is not normal is Q adjoin a real cube root of 2, or any cube root of 2, pick your favorite, over Q. This will not be normal if, for example, if this is the real cube root of 2, then this polynomial t cubed minus 2 is an irreducible polynomial over Q that has one zero here, namely the real cube root of 2, but it doesn't have the other ones, as the other ones are complex. And furthermore, if you chose to add in one of the complex cube roots of 2 instead to Q, then you could do it. There's another argument you could use to show that this polynomial only has one of the zeros and not the other two. You could use like a degree argument or something like that. So, this seems to rely on the cube root of 2 being real. It doesn't. Okay. So that is a non-normal extension. And let me just remind you that when we had this non-normal extension, we computed actually the Galois group of this in the last chapter. And this guy had Galois group just the identity. There was no non-trivial automorphisms. And the reason why that was is because the cube root of 2 had to go to a cube root of 2, but there's only one in this field. And so basically that forced it to be the identity. And so the degree of the extension is certainly 3, but the Galois group only has one element in there. So there's an inconsistency. And the reason for the inconsistency is that, well, one of the reasons is that it's not normal. All right, so let me actually get rid of this real quick. Now, I claim here that Q adjoin I over Q is a normal extension. And the question is why? Why is this guy normal? Well, what do we need to do to show that something is normal? Let's look at the definition one more time. It says, suppose you have an irreducible polynomial over the base field that has at least one zero in L. Then we need to show it splits in L. So let's do that. Let's take an irreducible polynomial over Q with a zero in Q adjoin I. So we have some P plus QI here. That's a zero of F. Okay, so that's all that we've written. Now, some things can happen here. If Q is 0, then T minus P is irreducible with P as a 0. But since F is irreducible with P as a 0, in fact, this is the minimal polynomial of P, this tells us then that actually F has to be a multiple of P, T minus P. Right, because they're both irreducible with P as a 0, so they're both related to the minimal polynomial, so they have to be multiples of each other. Otherwise, what's the minimal polynomial of P plus Qi? Well, if we let T be P plus Qi, or actually I don't want to do that. What do I want to do? I want to look at T minus P plus Qi, and then T plus P plus Qi. T minus P minus Qi, rather. And what are we doing here? We're using the fact that if P plus Qi is a 0, then the conjugate should also be a 0. So let's just multiply this out, and we'll see that actually we can put an equals here. But let's leave it a question for now. So we get t squared and then minus the sum of the constant terms times t. The sum of the constant terms is 2p because the qi and negative qi disappear. And then it's going to be this complex number times its conjugate. Great. So this is a polynomial over q. Certainly, there's no more i's in there. With p plus qi as a 0. And since p plus qi is an honestly complex 0, this polynomial has no zeros that are rational. So this must be irreducible because the degree is 2. When you're degree 3 or less, irreducibility is equivalent to having a 0. When degree 4 or more, you have to actually do more work. All right, so here we go. So let's see. We have an irreducible polynomial with p plus qi as a 0, but f is also irreducible with p plus qi as a 0. Oops. So they must actually be multiples of each other. F is some lambda times the minimal polynomial. So we actually know all the zeros of f. What's the other zero of f? The other zero of f is the conjugate, because it's the same as the zeros of the minimal polynomial. And both of these are in Q adjoin I. Okay, so if we had one zero, p plus qi, we must have all other zeros. In this case, there's only one. So Q adjoin I over Q is a normal extension. And let's just notice how difficult this is for, well, it's not that difficult. We have to rely on minimal polynomial knowledge and whatnot. But for such an innocent definition, all zeros or none, for any irreducible polynomial, there's a lot of work even in the simple case. Imagine if we have like a degree 6 extension or a degree 3 extension. How do you find all the zeros, right? It's tough. So later we're going to have a theorem that's going to allow us to show something is normal by doing a simple check. So this looks hard now, but we're going to make it easier in a little bit.